I think everybody's here, right? So it's my pleasure to introduce Gilles. Well, second partner of the dynamical duo here, Danie and Gilles. I'll let them choose who's who. Uh, and who's gonna make like this magical trick and tell us in a simple manner what the labeled Leavitt path algebras are.
Yeah.
So, so thanks, Gilles.
Okay.
Please.
I want to thank the organizers for the invitation and thank Danie for the last two talks. So today I'm going to talk about this left labeled path algebra. So Leah is introducing you to the left path algebras. And I want to try to motivate a little bit about the definition of these left labeled path algebras and how actually they generalize the the usual left path algebra. And myself and Danie, we are actually coming from operator algebras, and left path algebras also has a very motivation on sister algebras. They took the graph sister algebras and realized that there are some similarities that can be done. So I'm going to talk before I go to the definitions. I just want to briefly go through to the history of this area. And there are a lot of algebras that we can define. So first, I'm going to talk a little bit about the sister algebras. I think a good start point is what we call the Kuntz algebras. They are kind of the analog of left path or the left rings or left algebras. Leah has told about you, I think this morning already. And then we as mathematicians, especially with people from algebra, really like to generalize things. So there are a lot of generalization of these algebras. I'm going to quickly go through a few of them. But the idea is that these algebra that Kuntz defined, they're really dynamical in nature. So he worked with Krieger, who was a guy from symbolic dynamics, and then defined this new kind of algebras associated with what they call these topological Markov chains. And really, this from people who know symbolic dynamics, it relates with what we call the subshifts of finite type. So, as I said, Krieger is really a guy from symbolic dynamics, and then they define these algebras. And then they show that there are some properties of the algebra that can be found using properties of the dynamics and vice versa. So you can find invariants for the dynamics using the algebra. So there's this really interesting notion between looking at the algebraic version of things and the dynamical version of things. And then already in the 80s, because again, from people that know symbolic dynamics, if you have a sheet of finite type, you can describe this using a finite matrix of 0 and 1s, or you can describe this using a finite graph. So already in the 80s, they tried to study these Kuntz-Krieger algebras using graphs, but really things starting to come back. And then from there on, there are a lot of works on graph algebras in the late 90s. And the idea is that we're not only considering finite graphs, but you consider also infinite graphs. And the trouble at the beginning on how you define the graph algebras. So there are some restriction on the graph. At first, it was not for any graphs, but then they're starting to remove these restrictions. And then, well, then you have a lot of other generalizations. So as I said, these Kuntz-Krieger algebras, they are shift associated with subshifts. So you can define a algebra associated with any subshift. Then again, these algebras can be defined using a finite matrix of 0, 1, so you can go for infinite matrices. And then it turned out that these axolotl algebras, that infinite matrices and infinite graphs, they're not exactly the same class of algebras. There are some differences. So Tom Ford generalized these two in a new class of algebras that they are, so they include all the previous, except for the shift algebra, they include all the previous one. And then based in past, they define this algebra for labeled graphs, then includes all the previous one. And then you can consider also subshifts of one-sided subshifts. And then you can go for Boolean dynamical system, because we're gonna talk a little about this when we talk about these labeled graphs, algebras. There's kind of a Boolean algebra is gonna play a really important role, and then the dynamics can be seen as a dynamics on the Boolean algebras. And there are a little bit more general, these generalized Boolean dynamical systems. But this is the picture of, and this is just a part of the all the algebra that are defined since Kunz algebra. There are other things like separated graphs and all other stuff. So today I'm going to talk about the algebraic version of these labeled graph sister algebras. But then we have the motivation from the left path algebras. So this is the work of Leavitt. So Leah was talking about this today, is that you want to rings that you don't have a well-defined basis. So you have rings such that the ring is isomorphic to the ring direct sum with itself. So whenever you have a well-defined basis for any module, you say that the ring satisfies this invariant basis number. And then Leavitt was interested in understanding the nature of these rings, which does not satisfy these invariant basis properties. And then one way that he defined, so he defined this as an algebra over a field satisfying certain relations. And then people realized that the relation that Leavitt left to use it, at least for a class of the relations, really was the same relation that Kunz used it for his definition. So they started seeing that this connection between the left algebras and the Kunz algebras, and then there's these, I think these two papers really were the one that started the left path algebras. That first they see this connection between left algebra and Kunz algebras. Then you can see it, well, we can try to do the same thing for Kunz-Krieger algebras, and then we can try to do the same thing for graph algebras. So really the connection between the sister algebra world and the algebra world is through these left rings or left algebras and the Kunz algebras, and then you have all the generalizations that we can go from there. And so there are generalizations for algebras for Boolean dynamical systems, and there are generalizations for autographs. And then what I'm going to talk about today is this generalization for labeled graphs. And if you just want to forget everything about sister algebra, just look at the pure algebraic setting. You can really think that these algebras are going to include the left path algebra that we see from a graph. But then there's another interclass of algebras, is that these commutative algebras generated by idempotents. So I'm going to give an example later in the talk that these commutative algebras, not all of them are graph algebras, but we can model using these left label path algebras. Okay, so this is just a brief history of the area. So there are a lot of work done, generalizing a lot of things, but I want to try to start slowly, and then at the end I'll try to connect with what Danie has talked about in the last 2 days using Groupoids. So, as I said, Boolean algebras plays a really important role in what you're going to do. And the definition, you can give us a very concrete definition of a Boolean algebra, just saying that it's a family of sets, which is closed into finite unions, finite intersections, and relative complements. So this is really what we call a generalized Boolean algebra. Usually when you have Boolean algebra, you want the whole set to be there, and then it's going to be closed under complements, not just relative complements. But for what we're going to do, we're going to work with this generalized Boolean algebra, which I'm just going to call it a Boolean algebra by itself. So as I said, this is a very concrete definition of a Boolean algebra, just a family of sets satisfying these three properties. And the first thing that we see is that the empty set is always there in this family, because if you take any element on the Boolean algebra and take the relative complement with itself, it's going to be empty. So the empty set is always there. And then the other comment that I was saying that we're not going to assume that the whole set X is going to be in the family. So it's not a Boolean algebra in the usual sense. It's a Boolean algebra in the generalized sense. And the idea here is that because if you look at the left path algebras, it's going to have a unity if and only if the graph is finite, or there's a finite amount of vertices. And if you don't want to work with non-unital algebras, then you need to work with these non-unital or generalized Boolean algebras. So examples, a very simple example is just to take any set and you take the family of finite subsets of this X. So it's really easy to see that if you have two finite sets, the union is finite, the intersection is finite, relative complement is finite. And if X itself is not finite, X is not going to be in the family. So really, we really need these generalized Boolean algebras for this to make sense. And this is going to be one of the connections that I'm going to give for the left-to-left algebras later, because really family of vertices is going to be what connects there. So I'm going to talk more about this later. And another example, and really this is all examples, is if you have any Hausdorff space, so a little bit of a topology here, we need some well-behaved topological space. So we need this Hausdorff space. And if you take B to be the family of all compact open subsets, so we need to be simultaneous compact open, then this is going to be a Boolean algebra. I really need the Hausdorff here because we want compact subsets to be closed, and then two things work nicely. And well, it could happen that there's only the empty set as a compact open. The empty set is always these two. It could be the only there. But usually the topological space that we are considering, for instance, when Danie talked about ample groupoids, you need a base of compact open sets. So if you need to have bases really have enough compact open sets. So as I'm going to show in the next slide, this is actually all Boolean algebras. So all Boolean algebras are of this kind. And there are other ways of defining Boolean algebras. You can define more algebraically. So you say that you have a set with these three operations, satisfying a list of axioms that we know from set theory. So the union is commutative, the union is associative, the intersection is commutative, associative, and there's a distributivity between these two operations. So really we just take all the properties that we know from set theory, put this as axioms, and then you can define a Boolean algebra algebraically. Or you can use order theory as well. It's another way of defining a Boolean algebra. Because if you have sets, you have a natural order given by an inclusion. And you can see that the union is nothing else than the least upper bound, so the supremum of the two sets. And the intersection is the greatest lower bound, so it is the infimum of the two sets. So we have this notion of elasticity, which has these two properties. And then you have the relative complements, and you have the least element, which is the empty set. So this is another way of defining a Boolean algebra using order theory. So depending on how you define it, as I said, everything is really the second example here. So why is that? Well, I've tried to talk a little about that. So this is a result known as Stone duality. So every Boolean algebra is really just a set of compact open subsets of a certain Hausdorff space, and this Hausdorff space actually has an awful compact open set. So this Hausdorff space is as a base of compact open sets. And how do we do this? So I'll try to give an idea of the proof. And this for people who have already studied topology, maybe we've already seen the notion of filters and ultra filters. So the idea is that a filter, this is a notion really can be seen really in order theory, is that whenever you have a family that's close in an intersection, so the infimum is of two elements is always there. And you want that whenever you have an element that is greater than something that's in the filter, then this element that's greater is also in the filter. So this is the notion of filter. Usually you want this filter to be proper, in the sense that it's not the whole family B. So you could add another axiom here saying that the empty set is not in the family. But I don't know, sometimes filters, we consider only these two axioms. And then I have the notion of an ultra filter. Then for ultra filter, I want them to be proper, so the empty set is never going to be there. We just maximal elements with respect to the inclusion of the of the filter. So basically saying that we never have a filter that is greater than an ultra filter actually is the same. So that's what maximum means. And so the set that we're going to define is just the set of ultra filters. So this is the set that's going to be our topological space. And we need a topology. How is going to define topology? The idea is that for every element in the Boolean algebra, you can define this set UA with just filters that contain that element A. And this is going to be a basis for a topology. And in this topology, all these elements here is going to be compact open. And if you take the map that goes from A to this set UA, it's going to be a Boolean algebra homomorphism. Actually, it's going to be a Boolean algebra isomorphism. So you have this, as I said, all Boolean algebras, in essence, they are compact open subsets on a Haldor space.
Gilles, sorry.
Yeah.
So in that example that you gave for a Boolean algebra of the finite subsets,
yeah,
we know what the stone dual is? Can we just...
Yes, it's just the set itself with this discrete topology.
The set itself. So the set of ultra filter is just the set itself.
Yeah, so every ultra filter is going to be the filter of all sets contain a certain point. And then it's going to be the set itself with the discrete topology. Okay, so because I'm talking about a duality, so here we start from a Boolean algebra to build a topological space and then get back the Boolean algebra. We want to go the other way around. Start with a topological space. We have the Boolean algebra, which is the compact open subsets. And then when we recover the topological space. So that's the other part of the duality, is that if you start off Haldor space with enough compact open sets, so we need the base of compact open sets. And if you take the B as the Boolean algebra of all compact open subsets of X, then the dual of this Boolean algebra is actually homomorphic to the original topological space. So we have this topological space is completely characterized by the compact open subsets on there. And then again, how do you go? How do you do that? If you take any point on X, you can define a filter which are all the compact open sets that contain that point. It's really easy to see that if you have two elements that contain X, the intersection contains X. If you have anything bigger or something that contains X, again, it contains X. It's not really that difficult to show that it's an ultra filter. I'm not going to do here, but it's not really that difficult. And because you have a basis of compact open sets, actually all ultra filters are of this form. So this is going to give us a surjectivity of a map. This is a little bit harder to show, but we can also show that this every ultra filter in the family is of this form. And then have the homomorphism, just take this point to this effect. It's really, because the space is Hausdorff, it's going to be injective, because if I have two different points, I have compact open separated the 2 points, so this map is injective, and this above shows that it's surjective. And via this map, we really can see that this compact open set A is going to be sent to the UA. So we really have the Boolean algebra homomorphism before, and this gives us continuity, and the map is open, so it's a homomorphism. And so this is the kind of space that we then worked with when defining Steinberg algebra. So we wanted the unit space of the Groupoid to be a Haldor space where based on compact open sets. And this kind of space, we're going to call them stone space. So it's just a Haldor space with this base of compact open sets. There are other characterizations, a locally compact Haldor space which is totally disconnected, or a locally compact Haldor space which is zero-dimensional. But I think the easiest way of describing is just how the space is based of compact open sets. Okay, so this is the part of a little bit on topology and Boolean algebra. So why does this matters for algebra itself? So the idea is looking at these algebras generated by idempotents. So let's say you have, for me, R is always going to be a commutative unital ring. And A itself, it does not need to be unital, but here we're going to consider A to be a commutative algebra. So whenever you have a commutative algebra and you look at the idempotents of this algebra, you have a structure of Boolean algebra, which is given by these three operations. So the union is just taking the sum minus the product. With the product is just the intersection. So it's kind of really, I don't know, like counting elements in sets. You take the amount of elements in the first set plus the amount of elements in the second set, and we subtract the intersection. So really is what we are doing here. And the intersection is just the product, and this relative complement, you just take this, if you think of sets, just the set minus the intersection. And so this, because the algebra A is commutative, it's really easy to see that these elements are all idempotents, and then they're going to satisfy all the relations. If you go for an algebraic definition of Boolean algebra, this satisfies all the needed axioms to be a Boolean algebra. So idempotents in commutative algebras are always a Boolean algebra. So if you have Boolean algebra, as we've seen, you have a dual, and the idea is that this commutative algebra actually is going to be continuous functions on this stone space. We need a little bit more of a hypothesis. We need that A is going to be generated by the idempotents. And the second hypothesis is kind of torsion-free, but not for all elements on the algebra, but just for the idempotent. So we never have an element of the ring multiplying idempotent being 0. This should be only happens when either the element of the ring is 0 or the idempotent is 0. So it's kind of being false torsion, but not for all elements, just for the idempotents. So whenever you have an algebra like that, and you take the stone dual of the idempotents of the structure, then the algebra is just locally constant functions with compact support on this set X. And this algebra appeared in Danie's talks when they talk about groupoid algebras. And really here, if you think that X is a groupoid by thinking that every as an equivalent relation, which point is just equivalent to itself. So really, this is the Steinberg algebra of this groupoid X. So every commutative algebra satisfying this property is a Steinberg algebra. And we have done some work trying to characterize when algebras, not only commutative, but any algebra is a Steinberg algebra of some groupoid. I have some results on this direction, but I'm not going to talk about this today. Okay, so we have this commutative algebra generated by idempotents. Now, let's go and try to look a little bit more about these kind of algebras. And the idea is that these algebras actually have a really nice universal property, that they are generated by a family of elements associated for each element of the Boolean algebra. We satisfying these three relations, which are really, this last one says that each of these PA is going to be idempotent. So PA intersection A is PAA, so A intersection is A, so it's just saying that they are idempotent. The second one is exactly the same thing that we define as a union of idempotents. The first one, that we want to say that the empty set goes to 0. And so we can show that this locally constant function is really just the algebra generated by these elements satisfying these relations. And if we want to look at the Boolean algebra, since we also using relative complements, we can ask what happens with the relative complements. It's just that we don't need to include in the definition. It's going to be automatic that the projection of the relative complements is just this difference here, because we are asking that the empty set goes to 0. So it's really showing that showing this is just using these relations. We can use easily see that this holds. Okay, so why am I talking about this? Because when you go to the left path algebras, when you look at the vertices, you have the vertex. What were the properties of the vertices? That if you multiply the vertex with itself, it's just the vertex. And if you multiply a vertex with a different vertex, that's 0. So that's the axiom V that Leah told you about. And we can look at this relation if you consider X with the discrete topology. It's kind of what Daniel was asking. It appears here again. So if you have X with the discrete topology, and just for a shorthand notation, this unitary set we're just going to call Px. Then what do you have? That Px, Py is 0. So you can think that if you have different vertices is 0. I haven't written here, but it is to see that Px times Px is Px itself, so it's idempotent. And every compact open set of X, if X has the discrete topology just a finite set. So let's say A is this n points, then you can write the projection because there's no intersection between them, just this finite sum. So really, this algebra locally constant function on X, when X has the discrete topology, is just generated by the projection associated with each point. So pick this point as the vertices on the Leavitt path algebra. And then the relations, it's enough just to know that this is 0 and that Px square equals Px, so the Px is an idempotent. This is enough to find all the relations. So really, these locally constant functions, when X has the discrete topology, is just generate a projection associated with each of its points with the two relations, the B relations for the Leavitt path algebras. Okay, so now I'm going to go into the definition of a left label path algebras. So we kind of want to merge these two things. So we're going to merge this locally constant function with this universal property and the definitions or the axioms defining the Leavitt path algebra. But before that, we need a little bit more of definitions. We need to know what a labeled graph is. Graphs, we are working a lot of this during this week. When you, sorry? This one, this is just the direct sum of the ring indexed by X.
So it's a direct, oh yeah, but that many copies of it.
Yeah.
Oh, I see. Thank you.
So his question was just asking if, what's the locally constant function when X has the discrete topology, and then the answer is that this is going to be a direct sum of the ring indexed by the static X itself. Okay, so as I said, going back here, so graph is just this set of edges, vertices with a random source map, and we're going to label the graph. So what I mean by labeling, really we're going to label only the edges. So in combinatorics, you can label vertices as well, but I'm not going to consider labeling on vertices, just going to label edges. So what's labeling? We just take a set A, which can think a letter or symbols or our alphabet, and we take a function that's going to give each edge a symbol associated with it. I'm going to give an example in the next slide, but it's just putting a symbol in each edge. And this page is going to be called a labeled graph. And well, we already have the definition of a path in a graph, just walking on consecutive edges. And we can extend this labeling from the edge to paths. We just look at the concatenation of the symbols that appear, then it's going to form a word that you just read the symbols instead of reading the edges. And any element that can be found in this way, I'm going to call this a labeled path. And there's another definition that I'm going to need, because when you talk about CK2, the relation on the Leavitt path algebra, we need the source. We're not going to have the source of the vertices inside the algebra. So we're going to play the raw source as some sets of vertices. And then we need to look the kind of edges that leave this set. But we're not interested in the edges, we're interested in the labels. So we look at all edges that start in A, and you look at the label of this set. So I'm going to give an example, but this is going to play the role in CK2. We're going to use this kind of sets. And just a little bit more of definition that we're going to need. We have this notion of a relative range. So the idea is that if you have a path and you have a set, again, A is kind of like of a source of the edges that we're considering. So you look at all paths that start in A, and has, when you look and walk on the path, it has this label alpha, and you look at the end of this path. So the range of each of this path, which has the label alpha and start A. And if you consider the empty word, I think I forgot to mention this in the previous slide. And also, since we are not labeling vertices, we need this empty word kind of play a role of the labels on vertices. And for the relative range, when you don't walk anything, so you stay still, if you just the relative range is just the set itself. In particular, if you start any place in the graph and you walk through alpha, then you have the range of the labeled path alpha. So let's give an example. So let's say you consider this graph. So we have these three vertices, these edges, and then you have the labels. We're only using two labels, 0 and 1s. And from people from Topological Dynamics, maybe they can recognize this labeled graph, which is the graph of the even shift. So what are the labeled paths? So the paths are sequences of 0 and 1s, such that between two 1s, you must have an even number of zeros. Why? Because let's say you start 1 here and you want to add a 0. So the only way of adding 0 is going through this edge, going from V1 to V2. And once you are in V2, there's one option that is going back to V1, but when you go back to V1, it must be 0. So if you want another 0, you have to go to V2, then you have to not only want 1 0, but 2. So whenever you add zeros after 1, you need to add an even amount of zeros. And on the next one, you either go back to V1 or go to V3. So there's only an even amount of zeros between two 1s. So this is the labeled paths in this graph. And when you go back from 1 to here, you only have zeros, you can't go back to 1. So this is the labeled path that you have. And in Symbolic Dynamics, this is the shift associated with the labeled graph is called the even shift. Okay, so let's see a little bit of the definitions that we've seen above, this relative range. So let's say you have these two vertices, V1 and V2, and we'll take the relative range with respect to 1. So what do? You look at the V1 and V2, you look at all edges that leave these two vertices, and you look at the labels. So in V2, there's only one vertex leaving, which has a label 0. So this V2 won't play any role in this relative range. But when you look at the V1, there's an edge going back to V1 with label 1, and there's an edge going to V3 with label 1. So you look at these two ends of these edges, so V1 and V3. So this is going to be the relative range. Or another example, let's say you look at the V3, again, you look at the 1, but there's no edge leaving V3 with label 1, so this relative range is the empty set. Or if you want to look at the range of let's say just 1, well, there is one edge with label 1, which ends in V2. There's one edge with another edge with label 1 ends in V3. Here should be V1 and V3. Sorry, there's a typo here. This should be V3. And another thing that we need to understand is this label function here. So this is, we look at all paths starting, or all edges starting in V2 and V3. So there's one edge here. In V3, there's only one edge as well. And we look at the labels of these edges. So here we have label 0, here we have label 0. There's no edge leaving V2 or V3 with label 1. So this is the label of the edges leaving the set A. Okay, so this is an example just to try to familiarize a little bit with these definitions. And I think now we can I actually need a little bit more. So the idea is that for the definition of the algebra, not only we're going to use the labeled graph, we're also going to use a Boolean algebra inside the set of vertices, so Boolean algebra of sets of vertices. So we have this B inside, so here is the power set of the vertices. And we want to satisfy certain properties for this family. The first one is that we want the range of all labeled paths to be in the family. We want this to be closed in the relative ranges. So all relative ranges are also in the family. And there's another property that we want to satisfy, is that you want the relative range to preserve intersections. This is not always true for any labeled graph. The union, you can see that's always true, that relative range always preserves union, but this is not always true. A very simple example of these two things would be, let's say you have just 3 vertices with 2 edges connecting these 2 vertices, and let's say you have 1 and 2 here, and let's say you have here V1, you have here V2. So if you take A to be just the set V1 and B just the vertex V2, well, the intersection is empty, so the relative range should be empty because they have no intersection. But on the other hand, let's say call this V3, so the relative range of A with respect to 1 is V3. The same thing for the other set B. So the intersection here is V3. So the relative range not always preserves in intersection. We need this to impose this as a property for what we want to do. So usually they call this weakly left resolving, but the terminology here is really not important. Just you have that relative range preserve this. And as I said, it always preserves the union. And if these two, also the relative range of the empty set is empty. And we can show that it also, once it satisfies this, it also satisfies that it preserves the relative complements. So really what we have here is a Boolean algebra homomorphism that it's important. And finally, in the definition of the algebra, we need that the equivalent notion of regular vertices. So there we need the sinks and infinite emitters. We have a kind of an analog here. We count the number of ladders leaving a certain set A, and we want this to be finite and non-zero, the number of, or this be non-empty. But not only for A itself, we want, this is more technical, we want this for all subsets of A, which is in the family. You want this to be, to have no sinks and not an infinite emitter. So this is what we call the regular sets. Okay, so when we define the algebras, as I said, we're not only going to need the labeled graph, going to need this family of sets B. And now we can go for the definition. So the idea is that instead of looking at only at the vertices, we're going to look at projections associated with each of the elements, or idempotent of each of the elements of B. Remember that when you have these finite sets, you have the vertices, you can really see this as a sum of the vertices inside the left path algebra. And the other thing is instead of looking at edges, you're going to look at the labels. So we forget the edges on the graph. We look only at the labels. Since I come from sister algebra, I don't like to write the vertex itself as an element of the algebra. So I use this P and S instead of looking at the vertex and the edges inside the algebra. But it's just a notation. Okay, so the first part of the definition is just what we've seen before for that locally constant functions on X, that the projection of the intersection should be the multiplication of the projections. And when you take the unit, just take the sum minus the projection on the intersection, and the empty set goes to 0. So this first part of the definition corresponds to the axiom V on left path algebras. And then we have the second part of the definition, which I think they are called these E1 and E2. So we have the ghost edges and the edges. But since we don't have sources here, it's a little bit more tricky to define. But really what this is saying, if you think that A is kind of a source, you have the source multiplied by an edge, being the edge, but we don't really have that. But the idea that when you look at the range, instead of looking at the range of the edge itself, you look at this relative range of the set A. So it's a little bit more complicated, but really what this is doing is generalizing the axioms E1 and E2 in left path algebras. Then this condition 3, I think Leah called this CK1, which is given the property of being a partial isometry. But because we don't have source, we're actually going to need to spell it out as a partial isometry. But this is just saying we can have some kind of orthogonality between the letters in the alphabet. So if there's the same letter, you get projection on the range, and if you have different letters, you get 0. So it's the same as the properties I think Leah called CK1. So the fourth one, in the graph case, is just a consequence of things that came before, but here, as I said, we need to really spell it out and say that this is a partial isometry. So we have this SA star being SA, and if you take the star, same thing, the same thing. And the last axiom is the generalization of the CK2. Again, it's more complicated because I have more structures, but really what we're looking at is you have this A, and then you look at all the edges that leave A and just take the labels. We usually would have SA star, but because, again, we have more structure, we need to put this projection in the middle. But B here, as I said, this first one is analog of axiom V. The second one is the analog of E1 and 2. The third one is CK1. The fourth one you need to impose because in the graph case it's a consequence of the other ones, and this last one is just CK2. So it's a little bit more complicated, but we have that both left path algebras and commutative algebra generated by adipose are going to be examples of this construction. Okay, so how do we see? Actually, before we do that, so Leah was talking a little bit about grading this morning. In that left path algebras has a natural Z grading. Here it's going to have the same thing. So we never have these left label path algebras. We have a Z grading, which is the same thing that she said. We have a little more, instead of looking on only as on paths, we look at label paths. But it's the same thing that she said there. We just take the length of this path alpha, we take the length of the path B, we take the difference. We can see that the left label path algebra generates elements of this form. So we have this natural grading, as you have the natural grading for the left path algebras. And one really important theorem, not only for these left label path, but for left path algebra as well, is what we call this graded unixity theorem. Is how do you prove that a certain homomorphism is injective, which is related to what Leah was talking in the morning, because she gave a lot of examples of different graphs would give the same algebra, but not only look at when you look at the grading. If you look at the grading, there are really different things. So the grading plays an important role. And here we have a theorem that allows us, here should be phi, allows to give a kind of a easy to check definition to see when homomorphism is injective. So if you want to give different models for these level path algebras, what you do, you build a homomorphism using the relations and generators and all that stuff. As Danie has done this yesterday for left path algebras, he has shown how do you go from left path algebras to the groupoid algebra. You just look at what should the generators look on the other side. And if you show that this homomorphism is graded, and you show this definition that projections
Okay. Sorry, a very quick question because there's something I'm curious about this graded uniqueness theorem. Since a Z-graded algebra is essentially a comodule over the group algebra, is this related to the Heinemann-Wheeler theorem, which says that a morphism of, let me remember correctly, a morphism of graded object is injective if it is injective on the component of degree 0?
I think so, yeah. But I think here actually is a little bit weaker than being injective in the component of 0. Because here, if you take the component of 0, you're also going to have this SA in S alpha star. And here we don't need that. So it's a little bit weaker than being injected on the 0 component. We can look at something really smaller, but yeah, probably it's going to be related to this result as well. Because I'm going to talk a little bit more about this tomorrow. Is that we have a partial action that describes this kind of algebras, which is going to give us a grading by the free group as well. And then it's not going to be the 0 component, but it's going to be the component with respect to the identity of the free group. So these PAs here is going to be a component in a smaller grading, a more finer grading than the Z grading here.
Okay, thanks.
Okay, so as I said, this theorem is really important if you want to give different models to these algebras, because it's a way that we ensure that the map is injective. You don't need to look at all algebras, just need to look at the projections. And then whenever this is different from 0 for non-zero elements and non-empty sets of the family, then the map is going to be injective everywhere. Okay, so let me give a few examples. So the first example that I want to give is the graph algebras. So how do we define the labeling and then all the family? So the labeling is just going to be the edge itself. So you have an edge. The label is going to be the name of the edge itself. So we take the alphabet to be the edge, and then the labeling is just the identity map. And the family that we're going to consider is this family of finite subsets of vertices. Because as I said, when you take this family of finite vertices, really what you have the projection is the projection on the points of in this case E0. So it's going to be just the vertices on the graph. So how do you meet the map? As I said, so if you have a projection associated with a finite vertex or finite set of vertices, you just take the sum in the left path algebra. So here inside is the left path algebra. Since the labels are the same as the edges, you just look at the edge inside of the left path algebra. And then we have to show that it's well defined. So you have to show that these things satisfying the relations, defining all the 5 relations, and defining left label path algebras. And it's not really difficult to show this. We just have to observe that the relative range in this case is going to be the range whenever the source of the edge is inside A, or otherwise it's going to be empty. And then if you go to all the relations, they really translate really well from one to the other. And it's easy to see that this map is surjective because you have the generators of the algebra. We're going to have the vertices, and we're going to have both the edges and both edges. And for the injectivity, you just show that is use the graded uniqueness theorem, because if you take you multiply the sum of v's, because v's there are linear independent. So if you multiply by any element of the ring, it's going to be different from 0. So whenever this element is different from 0, so we can use the graded uniqueness theorem to show this is actually an isomorphism between these 2 algebras. So this is from a graph. You build a label graph. I have this family B, and you can show that this left path algebra is modeled by these labeled graphs. But you can go the other way around in some conditions. So we need a little a bit more hypothesis on the graph. We have this notion of being left resolving. So left resolving, we cannot have things like this that have two edges arriving at the same vertex with the same label. So for it to be left resolving, if we have these two edges, these labels should be different. And then label finite is just that each label appears only a finite amount of times. And if you have that, then you can show that actually and you take the family B again of being finite subsets, then you could go all the way around, that the left labeled path algebra is actually the left path algebra of the corresponding graph. I'm not going to go here to details after you can see when the slides are available. But the idea is that, again, the projections is going to be just the sum. And because the labeled graph is label finite, we can find what should be the label. We just sum the edges, which goes to that label. And the same thing for the ghost edges. And then again, we can prove that this gives us an isomorphism between these two algebras. But of course, we can ask if all left label path algebras are actually graph algebras. Because if they are all graph algebras, we don't need this extra definition. But the answer is no, because we have these commutative algebras generated by idempotents. And the idea here is that if you have a stone space, so a stone space have a Boolean algebra associated with that, you can define the edges as being just the set of the homomorphism, and we take no edges. So if you have no edges, we have no labels, and then you can show that the definition, all the 5 relations, actually what matters is the first one, because the other 4 you need the labels, but we don't have no labels, so we have just the first one. When the first one is just local constant functions on the set X. And something I think Leah haven't said this morning, or I think in her talk, I think she gave some examples. If you have just one vertex, then the left path algebra is just the ring. And if you have one vertex, just a loop, she gave this example, I think yesterday. So if you have just one vertex and a loop, this is called this Lohan polynomial ring. And we can show that if you have a left path algebra that is commutative, it's going to be a sum of copies of the ring and copies of the Lohan polynomial rings. It's kind of not really difficult to see that. It's just because if you have a thing like, let's say you have an edge that connects 2 vertices, let's say VE and W. On the one hand, VE should be E, but if you take EV on the other way around, it should be EWV, but WV is 0, so this is 0. So whenever you have an edge connecting 2 different vertices, we don't have commutativity, so we cannot have that. So we can either have a vertex itself, we can have loops, but you can't have different loops. So we have this EF. We can show that EF is different from FE. So again, it's not going to be commutative. So you cannot have 2 loops. You can only have 1 loop. So whenever you have something like that, it's going to be the polynomial, the Lohan polynomial ring. And you have a isolated vertex, you have just the ring itself. And because you have these joint components, then it's going to be a direct sum of these things. But when you go to this left labeled path algebras, because you have these more general studying where you can take any stone space and you take these locally constant functions, one thing that we can do is trying to, so you can try to find something that's not isomorphic to a direct sum like this. So how do we do this? For instance, we can take the natural numbers and we take the 1-point compactification of the natural numbers. So you can think as inside of the unit interval 0 and 1/n. So this is just the same thing as this compactification. And we take this locally constant function. This is not going to be a left path algebra for any graph. Why not? First, because this is generated by idempotents, the only grading that we can give this algebra is the trivial grading, because if you have an idempotent belong to Zn, and the square should belong to Z2n, where the square is the same as the element, so every idempotent must belong to the zero component. So you cannot have a copy of the Laurent polynomial ring, because as Leah has given the grading this morning, you have a Z grading, which is the natural grading, which is not trivial. So for it to be a left path algebra, you should be isomorphic to this direct sum. But this cannot be held, because this direct sum is just locally constant functions on a discrete space, which is the question that came before. So we cannot have these two things being the same, because the Boolean algebra of idempotence here should correspond to the Boolean algebra of idempotence here, which should correspond to the Boolean algebra of compact open sets on the set N. So since this compactification is not discrete, you cannot have this thing being isomorphic. So this is an example of left label path algebra, which is not a left path algebra for any graph. Okay, and then we said that we're going to have an application of groupoid algebras for these left label path algebras, but really it's kind of technical. So I'm just going to give very briefly how it goes. So the idea is that we have the Boolean algebra B, but for each labeled path, we can build another Boolean algebra, which is really an ideal of the Boolean algebra. So we just take the elements in the family that's contained in the range of alpha. So we have this Boolean algebra for each labeled path. And we can define two maps. So we have each alpha is going to have a dual. And for each ladder, you can define two different maps going from this. So this is the Boolean algebra, the Stone space associated with the ladder A. This is the Stone space associated with the empty word, which just B itself. And there are some technicalities that we sometimes need this to be empty. So the first one is just saying that the relative range is a Boolean algebra homomorphism, so we have a dual. So the dual is given by this form. As I said, it's a little bit more technical. And another thing is, since this algebra, Boolean algebra, is contained in B, we never have a filter in this algebra. You can just take the filter generated by this inside the whole B. So never have a neutral filter in an ideal of a Boolean algebra. You can find an ideal a neutral filter in the whole Boolean algebra. So they have these two maps. And we can kind of build up a graph from this. Not really a graph, it's going to be a topological graph. As I said, it's a little bit more tricky. And it's not really a graph, because the set of edges is going to be different from the range and the source. So we have instead of like looking at only one set is 0, we're going to have the set is 0 and net 0. And then we have the set of edges. So the set of edges is going to be this disjoint union. And we can use that maps f and h to define the source and range. And we're going to have, instead of looking at a graph, it's going to be a correspondence. Instead of looking just a graph itself, then going to have a topology. So have this notion of topological correspondence. And because E0 is contained in F0, the same thing that then explained for graphs, the bounded path space, we can do this for this topological correspondence. Again, we're not going to go through the details there. But we can define this boundary path groupoid. And this is the same thing that Danie had defined for graphs. This is going to work in this context as well. But now, because E0, F0, and E1 had topologies, and the topology on these has to take into account the topologies that we had there. But then, again, I'm not going to give the details here. It's much more complicated. But we can show that the left label path algebra is going to be isomorphic to the Steinberg algebra of this groupoid. And the idea is really very similar to what Danie have done for graphs, is that he said for each vertex you have a compactable bisection. Here is for each set A, you have a compactable bisection. Again, there for each edge you have a compactable bisection. Here for each lab you have this, and then we just can send the file of this projection on the correct function on this compactable bisection. The same thing for the essays, and then all the machinery that we do for graphs works here as well. And then these two things are going to be isomorphic. Okay, sorry for going fast here, but really this is very much more technical. I want to go more in details in the at least in the basic construction. Yeah, so that's what I have for today. So I'm going to give these two to reference. So a lot of what I talked about today is in this paper by myself, Daniel, Danie, and Juliano on this last path algebra for labeled graphs. And the construction of the groupoids, there's the one that we use in our paper actually is a different construction that we use in go from using inverse sum groups. But then this new definition is in another paper that I work with Eugene Kang, that we are working for this strategy of Boolean dynamical systems. Then we give a different definition of the groupoid. I think it's a little bit easier to understand. It's still a little bit more complicated, but that's it. So for today, thank you for your attention. And then tomorrow, we're going to talk about partial actions. So I think Hector talked about partial actions yesterday. I'm going to talk a little bit more about them tomorrow. And again, I'm going to talk about the cross product and how we can see the last path algebras as a partial cross product and all that stuff. And then connecting this with the, as for actions, we have a transformation groupoid. So for partial actions, we have also transformation groupoid. And then the partial cross product is again going to be a Steinberg algebra. So this is going to do tomorrow. Okay, so for now, thank you.
Any questions? Any other questions, right? There's some.